Okay, we have a gantry structure in the photo, and it's used to test the response of an airplane during a crash. We got a 8 megagram, remember that means times 10 to the third kilograms. And it's hoisted back until this angle right here is equal to 60 degrees. Then it's dropped, and it doesn't swing all the way down to directly underneath where it's hanging. It smacks the ground beforehand, and they can get different velocities by doing this. So they want it to come to some 15 degrees right there. We call one point A and the other point B when it turns to mush, and we're going to neglect the size of the airplane. Remember, we're just doing point masses. So this is actually pretty simple problem with conservation energy. They say determine the speed right before the crash and the tension. The max tension experienced. The max tension experienced would be right when it's at its fastest point, right there, right before it drops. So at B. So let's just start with T1 plus V1 is equal to T2 plus V2. Remember, V can be elastic and gravitational. We don't have any elastic though. So we snip it, and it's going to have some gravitational here at Y1. And you're going to have some new position down here at Y2. Or Y at A and Y at B, whatever you want to call it. Let's do Y at A and Y at B, because what we really want is delta Y. Alright, and the best method I would use to find this, the book doesn't go over it, is we have these two triangles right here, bing, bing, and bing, and this one right here. We know that it's 20 meters. And we have these angles. So if that was 60, that makes this then 30 degrees. And if this was 15, then this is 75 degrees. Let's keep up with the same color. 75. Okay, what we can do then, the way I see it, we're going to need that change in distance, delta y. We can either put this in as its coordinate beforehand, coordinate after, and this, I don't know, this problem doesn't make sense to me unless we call this y0, so I'm just going to show you how I do it. If I call that y0, then I just need to know this delta y, and that's really just the difference between the altitudes of these triangles then. Difference between the two altitudes. The altitude of this triangle right here would be equal to 20 sine 30, and this one right here, the larger one, sorry, would be equal to 20 sine 75 degrees. If we take the difference of those, 20 sine 75 minus 20 sine 30, that's going to give us this chunk right here, and that's how much it fell. And that is equal to what we're going to call delta y. And why do we need that? Because that's our potential, that's our we're going to get energy from that potential energy, from gravitational potential energy, and it's going to turn into velocity right before it crashes. That's all we care about, is right before it crashes. So here we go, 1/2 mv initial squared plus mg y initial, or we could do delta y, we'll call it y1. This ends up being, we'll call it y1, and there we go. And this is going to turn into some 1/2 mv final squared plus some mg at y2, and we called y2 0. Cross it out. We said it started from rest. Cross it out. The masses don't seem to be important, and we get the velocity is equal to the square root 2 times gravity times y1. So you just need to calculate this distance that it falls right here, y1, and that's it. We now have the speed, ends up coming out to 13.5 meters per second. And you could find the angle by finding the tangent to the path and make it into a vector if you wanted. But this problem, they were concerned with the max tension, and that max tension is going to be at the maximum speed, because we are in normal and tangential coordinates here. And if we look at the summation of the forces in the normal direction, the max speed comes into play because the normal component of acceleration is v squared over r, v squared over rho. Now, let's do a free body diagram. This is at 15 degrees right before it smacks the ground. This being the ground, not an axis of which we have an acceleration. So this would be the normal direction and the tangential direction. We have a tension holding onto this plane, and we have mg pointed down. And we get a component of the cosine theta, where this is 15 degrees. And putting this back together, we have tension pointed up, a mass times gravity times the cosine of 15 pointed down, and that's all going to equal to the mass, 8 times 10 to the third kilograms. And what else? We have the speed right here. Boom. 13.5, all divided by our radius, which was a constant the whole time, 20 meters. Alright, put that mass in here, 9.81 in there. And you can solve for your tension. We end up getting a tension equal to 149 times 10 to the third newtons, or kilonewtons. Alright, from here on out, I'm going to finish this section by just doing example after example.